Hello everyone. Okay, so over the last couple of lectures we've been talking about memory, how memory is organized, what the internal structure of some simple memory might look like, how the number of locations determines the number of address lines required to access that memory, how the width of the words in the memory determine the number of data lines. And we've looked at it a little bit from the perspective of the computer as well. The number of bits on the address bus define the number of locations that the computer is able to uniquely address, and that number is 2 to the m locations, where m is the number of address lines we have available. And we saw a little bit, today we want to get into looking at how we use those address lines to to locate memory within the system. One thing that may be you may have found a little unusual up to this point is that we are dealing with systems, and we're commonly dealing with an IS2 system that has a 32-bit address bus, but we've been interfacing to memory that has much fewer than 32 address lines. So how do we decode the address lines of the CPU such to activate the appropriate memory chip when we're trying to access that particular area of memory? So we got a little bit of a preview. Okay, so let's again, our topic here is memory addressing, and we got a brief preview of that a couple of lectures ago in the following diagram, where we saw that we had just a really simple example of a 1-bit storage device. So it only needs really one address line. Really, it doesn't need any. It just needs to be selected. And this here example, we had a computer address bus that had 5 address lines, but yet we were able to, through some address decoding, interface that to select this specific memory location, and only that memory location, when we had a very specific address, in this case 00101. Okay, so let's look at some other examples of addressing memory, and as we get into that, let's jump right into talking about a memory map. Okay, so as we've been saying, the size of the address bus, the number of address lines in our bus, defines the address space of our computer. Okay, in fact, again, we know that and we know that m-bit address bus will have 2 to the m different addressable locations. Okay, but just because we have all of those locations available they're not necessarily all used or filled. Okay, and this is really common in the computers we use, regularly, whether it's your laptop or your desktop computer. The available memory that it's able to access is often not filled, because we want the option to be able to add different peripherals, to add more memory. And that's something we often do, is we add extra RAM. If the computer out of the box had all of its available space completely filled with memory, we wouldn't have the options to upgrade our hard drive or add more RAM, because there would be no more ability to address those memory locations. Okay, so a memory map shows the following. It shows what memory is installed in the computer. Really, that's the main thing it shows. Shows what memory is installed in the computer. And it's going to show what type of memory it is. So, some simple examples, whether it's RAM, ROM, maybe flash. You'll often see in microcontrollers, the memory map will show where the program memory is, in the area where you can your actual program can be stored to be executed. Also, the memory map shows the address range that's occupied by each of these different pieces of memory that are installed in the computer. Okay. Sometimes, so I'll say may here and just highlight this. It may also show the addresses that are allocated for I/O devices. Okay, this would be an example of what we call memory mapped I/O. Okay, and this is in fact how the NIOS 2 I/O is organized. Is it all exists within the same memory space. Okay, if we don't have I/O showing up in the memory map, let's say that I/O may have a separate I/O map. So just like the memory map, it'll show what I/O is installed, what type of I/O exists at each of the locations, and the address range that's occupied. And as I said, often we want to we may want to expand our system, add more memory, add more I/O, and as a result the memory map may change. So it's not set in stone. It is able to be changed as we make changes to the installed I/O and memory. Okay, so let's maybe look at an example of a memory map for a fairly simple 10-bit a system with a 10-bit address. Okay, and in this specific example, we're actually showing that the entire memory map is filled. There's no free space, and this memory map, in fact, isn't showing the type of memory at each of the locations, but it does show that there are 4 different blocks of memory, and that each one has 256 locations, and it's showing the range of addresses that each memory takes up. So we know that if a memory has 256 locations, well, then it's the addresses within that memory chip are going to go from 0 to FF for each of them. But from the perspective of the system, the first memory placed at the lowest spot in the memory map is going to go from 00 to FF in hex, and the next one is going to have to start at the next available address. So it's going to go from 100 to 1FF and so on, right, as we keep adding additional memory. One thing you might note looking at the 10-bit version of the address here is that for each of the 256 location memory, that the least significant 8 bits go from all zeros to all ones. In every case, all zeros to all ones, all zeros to all ones, right? And every value in between here, right, as it accesses all 256 locations. Okay, so it seems like those least significant 8 bits will be able to be interfaced directly to the 8 address lines on the memory itself. What we have to look at is, what do we do with these other bits? Because we do have a 10-bit address bus. How do we use those to select each of the, in this case, 4 memory? Okay, before we go there, one other thing I want to point out is, notice that these just say they're 256 locations. We don't actually, in the memory map, need to know or need to specify the width of the words in this memory, right? It doesn't actually matter. This could be 256 by 8, in which case each memory chip would have an 8-bit data bus. Maybe they're 256 location by 16, okay? Or maybe they're by 4, right? That the width of our data bus is not portrayed in the memory map, although knowing the system, you are generally going to know what size of data it's addressing when it addresses each location. Like in the NIOS 2, we know it's byte addressable, so it's addressing it has a 32-bit data bus, but each location actually specifies 1 byte of memory. Okay, so just something to think about. So the memory map doesn't explicitly state anything about the width of our data bus. Okay, so let's get back to looking at the two most significant bits in this 10-bit address. And one thing that hopefully you've noticed by now is, if we focus again on just this first memory, you'll notice that the two most significant bits stay the same for the entire span of addresses. The entire 256 addresses, those two most significant bits stay the same, and so on. As we look at the next memory device, the two most significant bits remain the same. And then looking at the third memory device, we see that the two most significant bits are unchanged as we move through all 256 address locations. Okay, so it seems like this is something we should be able to take advantage of. So if we look at what the associated hardware and the decoding logic that controls the this hardware might look like, let's have a look here. Okay, I'm going to zoom out a bit to so we can see this all at once. Okay, so on the top is our memory map, and on the bottom is the actual physical memory devices shown. Maybe they're each a 256 by 8 memory chip, and we see how we can decode the address bus to locate each of those memory chips at a very specific location in the memory map. Okay, so let me clean up this diagram here again. So let's focus on the first memory here. I'll circle in purple. Okay, so that's this memory. So again, it has 256 locations, so it's going to, the device is going to need 8 address lines to be able to access all 256 of those locations. Those address lines here will vary from address 0000, the next address will be 00000001, and so on until we get up to 111111 or FF. Okay, so those 8 least significant address lines can come from the system's address lines A0, A1, up to A7. But we said that this was a 10-bit address bus, so there's another 2 address lines that can't interface directly to the memory because the memory doesn't need 10 address lines. Those address lines, we see A9 and A8, can be decoded with some form of decoding logic to activate only the memory device that we want when appropriate. So we saw that in this memory map for this first 256 locations that the most significant 2 bits will always be 0. So we take advantage of that by creating a address decoding logic, right? So a NAND gate with active low input, so when we have a 00 here, we get a 0 out, which activates this chip select and selects this memory device, and only this memory device. All the rest of them will not be selected while the A8 and A9 are 00, right? Because this one, second one needs a 01, the third one needs a 10, the fourth one needs a 11. Okay, so and we can do this for each of the memory locations, right? The next memory location will be activated when the 2 most significant bits are 0, 1, and we see we've developed decoding logic that is a NAND gate that has an active low input and an active high input. So that will generate a low to chip select this when our addresses are within the range that I'll highlight here. Okay, so as long as the two most significant bits are 0, 1, this chip will be selected, and the remaining 8 least significant bits will be used to feed into these address lines that connect directly to the chip to access any one of the 256 locations. And then of course we can generate a read or a write as necessary to pull data out of the device or to write data into the device. Okay, like in the process we showed with our read and write operations earlier for some of the more simple devices. Okay, let's I talked about this a bit in previous classes, but let's just look at it here since it's kind of relevant to this particular memory map. And what I want to talk about is a means of using multiple memory chips to construct the word at a specific address. Okay, so really if you think about it, this is not much different than creating our multi-bit registers out of the single bit the single bit memory storage elements that we looked at previously. Okay, so just let me bring up, right, just like this one, we made this each of these locations changed where we started with just a single bit storage element. We expanded that in this example to a 2-bit storage element simply by sharing the write lines, sharing the read lines, and in fact sharing the clock lines, the chip select lines. Now this one has also multiple locations, so becomes all part of the chip select. In this case, is able to chip select a number of locations, just like the memory chip that I've shown up above here. But so let's get rid of this, and let's focus on this one for a second here, just to address what's going on. Okay, so again, each one of these memory elements has 1K locations, or 1024 locations, and we can address all of those locations through the 10-bit address bus. But at each location we only have 4 bits available, right? Oops. And that's the same for both devices. Each one only has 4 bits available, but has 1024 locations. But if we are trying to interface this memory to a system that has an 8-bit data bus, there's nothing stopping us from using 4 bits from one memory and the other most significant 4 bits from another memory. And if we have both of these memories selected, chip selected, at the same time, right, which we can do by tying their chip select together, well, when we're addressing a location when we're addressing a location now in one memory, right, so let's say we put in some arbitrary address. Well, that address is these address lines are tied to the same address bus, so the address is going to show up on the address lines of each of these devices, and whatever other address lines might exist in the system will create the chip select for this system. And so therefore we have both devices able to be either read or written simultaneously. And now whatever data comes in on the data bus, let's say we're doing a write, well, the most significant 4 bits will go into this device, the least significant 4 bits will go into this device. Okay, and then the same when we go to read from this device, the most significant 4 bits will come from this device, the least significant 4 bits will come from this device because they're tied to the least significant 4 data lines. These bits are tied to the most significant 4 data lines. Okay, so this is pretty common in RAM memory. You'll see that the RAM will have multiple 8-bit wide memories that are connected in parallel, such that the 64 bits are contributed from 8 different memories that are all selected and addressed simultaneously. Okay, and so let's just look at this in a real application. I think it's interesting. Thanks to Wikipedia for providing a high enough resolution photo that we can read the part numbers off the actual chips that are used on a stick of RAM. So here's well, in these days, a bit of a small stick of RAM, 2 gigabytes, and let's see if we can relate what's going on here, how each of these chips of RAM that are actually physical chips that are on the board, the little black squares, relate to the 2 gigabytes. Okay, so I managed to find the data sheet. If you note back here that the part number, I don't know if you can see it on the chip here, is E1108 ACBG. Okay, so if we go over here, the E1108 ACBG says it's 128 meg words by 8 bits. Okay, so it's actually 128 megabyte RAM chip. And notice they're calling them 1 gigabit RAM, and they are, right? 128 meg times 8 bits would be 1 gigabit, right? And they're available in different configurations, 4-bit wide, 8-bit wide, 16-bit wide. Okay, but in our case we have the 128 by 8. So let's go back and look at this and see if that makes sense. So first of all, they're each have an 8-bit wide data bus, and notice that there's 8 per side. Okay, so I mean, I can't tell for sure, but my guess is that all 8 of these chips on maybe one side, whether it's one side of the board or maybe all on the left, all on the right, have all their chip selects connected in parallel, such that each one of these, maybe let me take a screenshot here so I can draw on it, right? Each one of these memory chips would be contributing data to the data bus simultaneously, right? So maybe this one here is contributing bits D7 to D0, and this one's D15 to D8, and so on until we get up here to D31 to whatever, and the most significant bit. So here we've got what seems like probably 8 chips connected in parallel, sorry, not to 31, to 63. right? Because 8 chips, each with an 8-bit data bus, we have 64-bit wide, which makes sense because most of our desktop computers these days would be 64-bit computers, which means they have a 64-bit data bus. Okay, but let's see how does the memory size relate to the 2 gigabytes of memory that it says that this memory chip has. So again, we'll recall that each one of these devices was 128 by 8. So each one 128 meg by 8. So actually each one's 128 meg. So 128 meg, 128 meg, right? For each of these, 128 meg. So on one side of the board we have 128 times 8, so we have a total of 1 gigabyte of memory, right? Each one has 128 meg locations and 8 bits at each location, so a byte. So each one's actually 128 megabyte. 8 of them makes 1 gigabyte. And then on the other side of this circuit board, we have another 8 chips. We can't see, but there are 3 chips. Oops, 3 chips that exist underneath this sticker here as well. We can just kind of see the top edge of them. So there is 8 chips on this side that make up the other 1 gigabyte of memory, for a total of 2 gigabyte, as is advertised for this RAM chip. Okay. Let's look at another example of a memory map that's not full. I said that for expandability purposes, we often have memory maps that don't have all the addresses occupied. So here's an example of a memory map from I want you to think about what is the number of address lines that exist in this system? Anybody? Can anybody think what there is? So stop. I'll give you a second here. Think about how many address lines this memory map is associated with. Okay, well, we can tell by looking at the range of addresses that are indicated in the memory map. So the memory map will always depict the entire range of addresses. Sometimes it'll just dash the lines and to show maybe large unused gaps in the memory, but here we see the total range of addresses. It goes from all zeros to all bits being 1. So 3FF is the largest address we can have. So this is in hex, right? This is 0x. So this 3 is 11. F is 1111, 1111, 1111. So you see that this is a 14-bit address bus. Okay. How many locations can be specified by 14 bits? Okay. Well, so we have M, which is our number of address lines, that is equal to 14. So we have 2 to the 14 addressable locations. Maybe right off you might think, well, I can't do that in my head. Well, 2 to the 14 is equal to 2 to the 10 times 2 to the 4. 2 to the 10 is, of course, 1024 or 1K, and 2 to the 4 is 16. So we have 16,384 locations, or maybe more easily stated, we have we have 16K locations. So this is this memory map is a memory map of a system with 14 address lines that's able to address 16K of address space. Okay, so with that in mind, can you determine how large each of these blocks of memory are in the memory space or in the memory map? Okay, well, if we look at this RAM is going from address 0000 to 00FF, right? So that is 0 x0FFF is equal to that, which is equal to 4,095. Okay. How do we do this? Well, you know your conversions, so you could do this directly from the hex, and in fact let me actually make this a little bit simpler. This RAM is going from address 0000 to FFFF, so it actually has, because we have to count the location 0, it actually has this many locations, right? Which is oops, sorry, one extra 0 there, which is simply FFFF plus 1 to include the address 0. Okay, so this is probably more easily to calculate how many locations that is, because we can calculate it as 1 times 16, right? This is base 16 to the 3. We're in the, right, this is 16 to the 3 location. This is 16 to the 2, 16 to the 1, 16 to the 0. All of these locations are multiplied by 0, so their values hold no weight. So 1 times 16 to the 3 is 4096 or 4K. Okay, so each one of these devices, this RAM is 4K locations, and this one is 4K locations. How do we know that? Well, we could do the math again here. Let's maybe this memory map isn't drawn to scale, so we could say, well, this one goes from 0x1FFF to or it goes from 01000 to 01FFF. Let me subtract the two values to find out what the range of values is over which it varies. But again, we have to add 1 to account for the first location. So we have a total number of address that's equal to 1000 and hex again, which is also 4K. So that RAM is also 4K, and we could do the same calculation here, but we see that there's a difference of FFF from the first address to the last address, so that also has 4K of locations. And this makes sense. We said this was a 16K memory down below here when we calculate it. So 16K divided into 4 blocks, 4K each. Yeah, it makes sense. So we actually have a total of 8K of RAM in this system and 4K of ROM. Now I don't know if those are bytes or because I don't know the word size of each of these memory devices. Again, that's often not indicated in our memory map because that's specified somewhere else and isn't essential to show in our memory map. Okay. Let's go back to back to one of our earlier sizes of memory and look at it interfaced to an address bus that's larger. So in this example, a 16-bit address bus. And we're back to a 256 location memory. So again, the memory itself has 256 locations, so it only needs 8 address lines connected directly to its own address bus of the chip. But we have to do something with the other 8 address lines that exist in this system that has a total of 16 address lines, such that we select this and only this memory device for a very specific address. So in this example, we'll see that this 256 by 8 memory is only going to be selected when we have these bits on the 8 most significant bits of the address bus. How do we see that? Well, we see this input's going to be active with a 0, this is active with a 0, this active with a 0, this with a high, this with a 0, high, high, high. Okay, so this memory device is going to be active for those specific bits on the most significant bits, while the 8 least significant bits are going to be able to vary from all 0, right, to when it is accessing the first location in that space, and the second location will be accessed here, and the third location, and the third, let's keep going here, and there's the third location, all the way up till when they're all FFFF. But again, the most significant bits during this entire time will always be this. So if we want to describe the address range over which this memory chip occupies in our memory map, we can think about, well, okay, the first location of this memory chip will be selected when the most significant bits are this and always this, and that the first location will be selected when the least significant bits are 0, and the last location will be selected when, again, the most significant 8 bits are precisely what's decoded by my decoding logic here, but the least significant bits can go up to being all 1s. Okay, so this is a value of, if we want to write this in hex, 0x1, 17 00 up to 0x17ff. Okay. Does that make sense that it occupies that space in the memory? Well, let's take those values and subtract them to see how many locations the chip is occupying in the memory map. So FF00. Okay, add 1 to account for the first address at 0. So we have a total of 0x0100 locations occupied. How many is that? Well, this is equal to 1 times 16. This is the 16 to the power of 2 location, which is 1 times 256, which is, of course, 256 locations. Yeah, makes sense. We said that this memory was a 256 location memory. Okay, seems like it would be a lot of custom logic to locate a number of memory devices within our system if we have these multi-input NAND gates which are built up for each chip. So here's an example of some decoding logic with the use of a 3-day decoder that could decode multiple 256 block locations of the memory map with just a fairly simple bit of hardware. Okay, so think about how this works for a second. So we're assuming a 16-bit address bus here again, right? And we're assuming we're generating chip selects for, well, like the memory above here, right? So I could pull, let me maybe bring this memory down here. Oh, did I get that? No, I did not. Okay, let's try this again here. Okay, so you can imagine this decoder might be used for multiple of these 256 location memory devices, and each one of these, I could put multiple of these here. Let me zoom out here a little bit. Let's move this guy down. Okay. Let me shrink him up a little bit. Okay, let's assume that there's a bunch of these that exist. Okay, I've just shown 2, but you could imagine that this decoding logic on the left exists to generate chip selects for 8 of these memory, right? So each of these chip select lines is going to come over and interface to the chip select line of each of the 8 of these memory devices. So let's think about how this works. Again, the least significant 8 address lines we don't have to worry about. Those are going to get decoded by each of the memory chips, but the 8 most significant address lines are going to get decoded by this 3-day decoder and some a multi-input NAND gate here. Okay, so this NAND gate will only have its output go 1 when the inputs are 0, 0, 0, 1, 0. Okay, so we've defined the upper 5 bits always have to be this, and now these bits A, 8, 9, and 10, since they're decoded through the logic, the 3-to-8 logic 3-to-8 decoder, they can go from value 0, 0, 0, which will activate this output, 0, 0, 1, which will activate output 1, and so on up to 1, 1, 1. Maybe I'll write these down here. Okay, so these bits here can go from 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, all the way up to 1, 1, 1, right? As we cycle through each of these locations being activated as we place the appropriate address on those inputs C, B, and A of the decoder. Okay, so as each of these addresses, specific addresses, these 8 addresses here are applied to the address bus, I in turn am activating these one at a time. I'm activating these outputs, right? So let's focus on just one of them. Okay, so when I when I have these most significant, these bits on the most significant 8 bits, output 0 will become active. That's going to activate the chip select for this first RAM or ROM or memory device. I guess it's a RAM. It can be written at least, so it's a writable device. And the least significant bits are controlled or connected directly to the 8 address lines on the device. So those can range from being all zeros to all ones. Okay, so for this, maybe I'll circle this in purple. For this particular device, it can have, it's going to be selected when my address is 00001, 00000, 000000000. So that's a value of, in hex, a value of 1000. And it will also be selected through all the range of addresses in the least significant bits up until we get to all ones, right? So that's 0x1 0FF. Okay, and there's what you see there. That output is going to select the device, a 256 location device, over this range of addresses. So it's going to decode this range of addresses in the memory map, and it's going to locate this device at those range of addresses in the memory map. Okay, and so on as we change bits 8, 9, and 10 to the next value. Maybe I'll pick a different color here, right? We're going to select this range of addresses, which will decode and activate the chip select for another 256 location memory. Okay, and all the way up until this last location, right? which is depicted by this memory, which is going to be able to go from this address all the way up to all ones. I should rewrite these as well. These are going to, the upper 5 bits always the same. These 5 bits, or sorry, these 3 bits are the bits that are activating output 7 here. So this particular memory is going to have be selected over the range of addresses of 1700 0x and 17 up to 17FF. Okay. So that depicts memory maps and a variety of different ways of decoding our address lines to locate memory and different forms of memory at specific locations in the memory map.